Alright, in this video, it's time to get back to some navigational elements. In this video, we are going to be creating the node class. The node is a class that can be connected to other nodes. We're going to create an object that is going to derive from actor, meaning we can place it in the scene and see it. But the sole purpose of this actor is to maintain connections to other nodes. Using this class, we will be able to build path networks. So we'll have the ability, you could say, to build a graph of nodes, to where the nodes can be followed connection by connection. Later, the node class will be extended to hold various information needed by the pathfinding algorithm. But in this video, the key is just to get the node class itself put together with all of the members necessary to manage an object that is connected to other objects, or in this case, other nodes. So to begin, we're going to go up to our project. We'll add a node class. Actually, we need to put an extra folder in place. We're going to organize all the navigational elements into their own folder, just for ease of reading. So I'm going to add a new folder here, which we will call navigation. Then into the new navigation folder, we will add a class, and this class is going to be the node class. We'll begin with our standard cleanup of our namespace. We need to add some using statements. So we'll put these in place as Microsoft.xna.framework and Microsoft.xna.framework.graphics. Now we can move on to the node class itself. The first thing we need to add is a field. We need to have each node to be capable of storing all of the connections it has to other nodes, and we'll do this using a list. We'll make a public list of nodes, so list of type node, which we will call connected. Then we will turn around and initialize this to be a new node list. As a matter of fact, let me actually throw a comment down here to indicate that this is really what is going to represent our path network, because the path network will be built out of nodes that are connected to other nodes. Now again, looking at this from a data perspective, this is really it as far as the concept goes. We have a class node that can be connected to any number of other nodes. Now, to make it a little bit more helpful, we're going to create a series of methods that will let us interact with this connected list in a more intuitive manner. Also, since this node is indeed an actor, if we were to attempt to build now, we don't yet have the code set up to tell the actor what texture it's going to use. So what I'm going to do is drop down a parameterless constructor that will properly feed in the node texture and node color. So we're going to make a constructor. As a matter of fact, before we do that, we need to note the fact that node does indeed extend actor. Because again, just as we said at the beginning of this lesson, we treat nodes as a special type of actor and therefore leverage all the current actor functionality. Now, if we build, you see, in addition to needing to set up the correct node texture, we also have to address the fact that actor doesn't have a parameterless constructor. So really this constructor is going to accomplish two things. It's not only going to set up the node properly, it's going to give node a parameterless constructor to make it easier to work with when we create nodes interactively. So we can create our public constructor as public node, then empty parentheses. Then we'll chain this to the base constructor using base, and here we need to feed in a texture 2D and a color. For the texture, we'll look into the style class, and we will grab node texture. For the color, we'll use style.nodeColor. Now, as far as additional code, we don't need anything else, so I'm actually going to put the method body just out to the side of the constructor. Now, if we build, we can see that this satisfies the requirement for these parameters in an actor constructor. And again, we now have a parameterless constructor when we're using the node. All right, now we can move into the various methods. Since everything is revolving around nodes being connected, we'll create methods that will aid us in connecting this node to other nodes or disconnecting it from other nodes. Let's begin with connections. Let's make a public void method called connect2, and then we will pass in a node reference using the node parameter. So the idea is that if we took node A and told it to connect to node B, passing node B in the parameter, we would like a connection to be established from node A to node B. We also want to make sure that we carefully manage this list and make sure we don't connect the node to another node multiple times. So before we establish the connection using the list, let's make sure it's not already connected. We'll do this with an if statement saying if not this dot connected dot contains the node that we're contemplating connecting, which is node. So if that node is not already connected to the current node, then we can proceed and connect it. So we can say this dot connected dot add, passing in the node parameter. So with that in place, that will take care of the connect2 method. Now we need the opposite of this, which is disconnecting. So we will make a public void method called disconnect from, and then we will pass in the node to disconnect. So the idea here is that if we have node A and we call disconnect from and pass in node B via the node parameter, then node A should be disconnected from this node. It should be noted that once again this is only a one-directional command, meaning if node B here was connected to the current node, that connection will be left intact. So what we'll do here is we'll look into the current nodes, this dot connected list, and we will remove the node parameter in question. Once again, remove operates completely fine if there is no instances of this node in the list, so we don't need to do any additional checks. Now, with both of these methods, once again, these are one-directional only. That means if we wanted to connect node A to node B and node B to node A, that would actually be two separate connections requiring two calls to connect to. This behavior is left in place so that if you ever wish to implement one-way paths between nodes, you can very easily do this, since the connections will always be based on the current node. Now, more commonly, you will want to have two-way paths between nodes, and that means with this set of methods, you would have to make two calls to connect to in order to get two nodes connected with a bidirectional connection. Now, in order to make this process easier, we're going to create some additional methods that will create bidirectional connections between nodes in a single call. We'll call the first bidirectional connect. So we'll make a public void method called bidirectional, which I'll abbreviate to BIDI, connect, again passing in a node parameter. So here we want to make two connections. So we'll take both this instance and the node and connect both of them together. So we can begin by saying this dot connect to. We'll simply use the method we defined earlier. So this dot connect to node and node dot connect to this. So we've established a connection on each of these nodes, which in navigational terms would be represented as a bidirectional connection. Now we also want the reverse of this. If we have two nodes and we want to break all the connections in both directions, we'll make a bidirectional disconnect. So we will make a public void method, BIDI, disconnect, taking in a node parameter. And just as we did before, we'll leverage the already existing disconnect from method, so we can say this dot disconnect from node and node dot disconnect from this. So again, if there were two connections between both of these, we will break both connections, leaving no connection in either direction from the two nodes. Alright, now there's one more aspect of actors that needs to be specifically addressed in node. Of course, actors can be arbitrarily deleted. We even went ahead and added an official delete method to the actor class. Now we need to make sure that nodes are aware of deletion. The reason we need to do this is whenever an actor is deleted, we need to make sure that any nodes that were connecting to that actor are alerted to that fact and have that node removed from their own connections list. Otherwise, we would end up with phantom nodes that have ceased drawing because they're out of the main actor list, but continue to be used in the navigation algorithm because the nodes are still connecting, and therefore the path network, looking at it as a graph, is still intact. So whenever a node gets deleted, we need to make sure that all connections to that node are removed. So in order to do this, we will override the delete method that's coming in from actor. We will leave the call to base.delete in place, since the base code for delete is what's actually going to remove us from the actor list. Now in addition to this, and before we get deleted, we're going to loop through all of the actors and make sure that any nodes in the actor list that are connected to us get disconnected. Excuse me. Now the method that we're going to use to loop through all nodes is a little bit interesting here. We're actually going to leverage some of the link functionality, the language integrated query, in later versions of C#. So we're going to write this down in using one method. I'll note how we would go about doing this if we were using an earlier version of C# that did not have link functionality. Because the scenario we're about to run into is we would like to loop through all nodes. But as far as our data structures are concerned, we don't have a list of all nodes. We have connected that is local to individual nodes, and back in actor, if I briefly jump over here to actor.cs, we have an actor list, but that's everything. That could be monsters, enemies, other actors that we create in the scene. As far as connections are concerned, we want to make sure that we only loop through nodes. Now there is a filter method available as an extension method as part of link that will allow us to walk through a list of objects and filter out based on a type. That way we can take the full actors list and filter out only nodes and then iterate over those nodes. Now we can do the iteration using a for each loop. So we can say for each var node in actor.actors. Now we can take this actors list and look at some of the methods, and you can see some of these methods being indicated as extension methods by the arrow next to the method icon. If we scroll down near the bottom, we have an extension method called ofType. So we can invoke actors.ofType, specify the type to filter by. In our case, this is node, and then give our opening closing parentheses to indicate the method call, and then that will take care of the actual call to ofType. OfType should return an object that can be iterated over using the for each loop. And then of course each of those things coming out of the iteration should be individual nodes, since that's the type that we filtered by. Now inside of our for each loop, since we're conveniently seeing only nodes, we can simply take the nodes and issue a disconnect from, feeding in this. Again, back to the topic of deletion, these are going to the nodes that still remain, making sure they break connection from this, which is the actor that's being deleted. Now, very briefly, just in case anyone is running a version of C# that doesn't have the link functionality and needs to loop through all nodes, the way we would go about doing this would be looping through all of the actors, then checking the actors, seeing if they're nodes, and then proceeding with the disconnect from. I'll type this out once just to make it perfectly clear. Later on we will be using this ofType filter multiple times, so I just want to show how this would be done if we only had the actor list. We could of course do a for each loop. We could say var actor in actor.actors. Then we could do a check. Since we're really looking for nodes, we could make a node local variable that is equal to the actor casted as a node. Then we'll do a check on the the node variable and see if node is not equal to null. Then we know that we have a node, and we could run node.disconnect from here. We can see if we build, this builds just fine. So this is the code that we would need if we didn't have the link functionality to leverage. In this case, our version of C# is working just fine with link, so we'll pull out the alternate method and simply rely on the ofType extension method. So, with all of this in place, we now have the proper handling for the case of a node getting deleted. So there's one thing left to do inside of the node class, and that is we want to visually represent the connections between nodes. We will do this by drawing lines between any connected nodes. So what we'll do is we will override the draw method from actor. We will leave the call to base.draw in place so that the proper texture gets drawn with the current color. But in addition to this, we're going to draw some lines. Later we'll be drawing other things inside of draw, so I'm going to drop down a comment saying that this is the section for lines. Now in order to draw lines, all we'll do is loop through all of our connections and draw lines to the connected nodes. So I will make a for each variable. We can say for each node in this dot connected. So going through all of our connections one by one, we will draw a line. So we'll look into the line class, we will invoke the draw line method, and we will assemble the parameters necessary to draw a line. We'll pass on the sprite batch from draw over to the line method. The texture that we'll use when drawing the line will come from style.fill texture. The color is given by style.lineColor. Now we need to feed in the two actors that the line should appear between, and that is going to be from this node actor to the node actor that we are looping through, the node that is representing this connection. Finally, we have a layer depth, which we are not yet using to differentiate layers, so we'll simply set that to 0. So we'll terminate that statement, build, and everything seems to build just fine. So looking at the code now, we have everything in place that we need for the node class. Again, a node can represent a connected graph, which we will use for a path node network. We've created utility methods to create and destroy connections. We have deletions handled cleanly, and we have the code necessary for visually displaying all of these connections. So that is going to take care of the node class, and in an upcoming video we'll begin putting these together using the scene editor. So that is going to wrap up this video.